All right, before I do that problem, I want to explain one thing about line charge densities. It's going to be important to listen to this. So if you have any line charge density that's infinite in extent, I'm just going to draw it this way. No, not this. All right, suppose it's up and down this axis. We'll call it the z-axis. And we're going to assume this is an infinite line charge density of rho L. Constant value, doesn't vary. From last time, you know that if you come out a radial distance, that radial distance has to be a perpendicular from there to the point of observation. That the actual electric field at this point is given as a magnitude of rho L over 2 pi epsilon naught magnitude of rho, where that would be, this is rho. It's a radial distance. It's actually a radius vector that's perpendicular to this, measured from this point to the point of observation. Are you with me on this? Now that's just the magnitude. To get the direction, it's times a rho. That's a unit vector in the direction of rho. You all follow me? Now this becomes very important when you're doing problems where the line charge may not be on the z-axis or x or y. It may be like, it might be at y equals -2 up and down the z or the x direction. All right, then I could ask for you. So then this radius vector becomes very important. Everybody got me on that? Now, whatever dimension is the infinite one, the point here, if you're looking for the E field, it doesn't matter. If this is the z direction, it doesn't matter what z is here because it's infinitely long. Do y'all follow me? The line looks the same, it's infinite. The other two coordinates matter, so keep that in mind. Now, when we talk about rho vector, it doesn't necessarily mean it's got to be cylindrical coordinates. That's just a vector. It's a way of denoting the perpendicular measurement from the axis to the point of observation. And in general, you could have it equal to the x coordinate there, whatever it is, call it x1 minus x on the axis, and this really is going to be meaningless, x2 ax, plus y1 minus y2 ay plus, and then z1, actually z loses meaning, doesn't it, class? Y'all follow me? Z's infinite, so you might as well forget z. Now, x1 minus x2, the z-axis is up, this is the x-axis, and this is the y-axis this way, if we were in Cartesian, right? So, if we're talking about x1 minus x2, I'm calling, remember I should say this is the E field at the point, x1, y1, z1. Now, if it's on the axis, on the z-axis, then effectively x and y are 0 here. Do y'all follow me in this class? Right? But they don't have to be. I could make this at y equals -2. I could make it at x equals 2. Y'all follow me? As long as it's infinitely long. So keep that in mind. I'm going to do this axis problem, but I wanted to bring this out. All right? And you know that, I mean, that's how you would get a vector, right? And then if that's the vector, how do I get a unit vector, class? Then I just take rho vector over magnitude of rho, correct? Y'all agree? All right, now let's do the problem that you asked about. You've got, this is the x, y, and z coordinate systems. This is the origin. Tell me, are the infinite charge densities are on the x and y?
X and y axis.
All right, so up and down here you get a line charge density, right? And here you get a line charge density. You got two of them. Same value? You can put down the value, but it really doesn't matter at this point. I think it was 5 microcoulombs or nanocoulombs. What?
Yeah, nanocoulombs.
5 nanocoulombs per meter. That's fine. All right. Now, what's the first point of observation?
It's 004.
Okay. So we're at x equals 0, y equals 0, z is 4. Right?
Yes.
want the E field. Now, the E field would be the E field from one line charge plus the E field from the other. Do you all give me that?
Yep.
Just think about this. Let me call this E1. So E1 here, first line charge I'll take on the x-axis. You realize I've already got a perpendicular to that point? I'm right there, correct? I'm just at a distance z equals 4 above it, right? Therefore, for this one, it would be rho L over 2 pi epsilon naught. And in this case, rho is simply 4, right? Correct, class? And what is a rho? A rho is a unit vector in the direction of rho. If this is rho, and I hope you all see this, this is perpendicular both here and here, right? It's perpendicular to both. It's straight above it. You all agree? So what is the unit vector associated with this E field?
AZ.
It's got to be AZ, right? I mean, we could go ahead and say, well, rho is going to be Z, right? AZ. And then we could get a unit vector. We take Z, AZ divided by Z. It's just AZ. All right, so this is AZ. What's the next one? Well, it's still rho L. It's still over 2 pi epsilon naught. And because we're at the origin, the electric field from the second one is the same as the first line charge, right? So this is just over 4, and then it's AZ. And by this time you can see, you might as well just write rho L over pi epsilon naught 4 AZ. So this would be E at the point 0, 0, 4 would simply be rho L over pi epsilon naught 4 AZ. And you can put the numbers in there, but that's going to be the answer. Do y'all follow me? It should be obvious. You gotta live with these things. Okay, what's the next coordinate?
It is
Whatever it is.
0, 3, 4.
Okay, this one's better. So now I want the E field at the coordinate 0, 3, 4, right? This one I'm going to spend a little time on. I want to make sure you see this. So I'm going to take the first charge distribution to be the one on the x-axis. Everybody with me on this? When I look at this, it's infinite in the x direction. So this would be rho L on x-axis. And what I'm going to do is I'm going to look straight down this x-axis. So when I look straight down the x-axis, I look like that. That's x. This would be y. And this would be z. And here's my line charge right there. Can you all imagine that, class? X is coming right out of the board, straight at you. All right. Now, where's this point, 0, 3, 4? Well, it's at x equals 0. And at what? Y equal 3. And z equal 4. Right? So it is right here. Y'all with me? That's where we want the E field. I'm trying to make sure you see visually what I'm talking about. So now your radius vector goes from this line charge, that's the z or the x-axis, to here. That would be rho vector. Do you all agree with that? Please focus here. This is so important. Okay? So what is rho vector? Remember, when you're getting a vector, you take the coordinates of the point of observation of the field minus the source point, right? In terms of x, doesn't matter. Take a look at this. The x coordinate here is 0, right? It's the orthogonal position of this line. It's 0 there. It doesn't matter, right? All right, what about the y coordinate? Well, it's 3 here, it's 0 here, correct? So that means you have 3ay. What about the z coordinate? 4az. Does everybody see that? plus 4az. Now this has to do with the line charge on the x-axis. Everybody got that? All right, so what's the E field gonna be? Just from this line charge, I'll call it E1. That's gonna be equal to rho L over 2 pi epsilon naught, right? Now you put the magnitude of rho in technically, right? What's the magnitude gonna be?
5.
Yeah, it's 3 squared plus 4 squared square root, or 5, right? Now it's times a unit vector, right? The unit vector would be this divided by its magnitude. Its magnitude is 5, correct, class? So it's really going to be times 3/5 AY plus 4/5 AZ, and that, in fact, is the electric field from the line charge on the x-axis. And I hope I'm answering your question in a way that's understandable to everyone. Now we've got to get the electric field at that point, 0, 3, 4, from the one on the y-axis, right? So what I'm going to do, I'm going to use this board right. I'm going to erase this. All right. Now, follow me on this. I'm going to look right down the y-axis. If you can, try to imagine this. If I'm going right down the y-axis, this is where my rho L is. And you think about it, if I'm looking straight down the y-axis, the x-axis would be in this direction, and this would be the z-axis. Just give yourself a minute. If x is coming, if y is coming out of it, normally it's x, y, z, right? Well, if you're looking down the y, the x right here is going to be in that direction, positive x. Can you all see that in your mind? Okay. Now, where's the point again? Well, that's the y doesn't matter in this one. It's at x equals 0, right? So x equals 0 is right here, isn't it, class? Correct? y doesn't matter. And then at z equals 4. Right here, right? Y'all follow me? Make sure you can visualize this in your mind, right? So what's the electric field from that? It's right here, right? This would be E2. Well, we could go ahead and we're going to do it anyway. We write down the equation, which is going to be rho L over 2 pi epsilon naught. And what's rho in this case? Just 4. Y'all see it's 4, right? So just leave it as 4, right? And what is the unit vector? Just by looking. How many see it's AZ? All right? You good with that? It's AZ. All right? Now, what's the total field? It's this field right here plus that field. And if you add them up, you're going to see, what does it come to? I'll put E total over here. It's going to be, well, I have rho L over 2 pi epsilon naught times 3 over 25 AY. Plus, and then I have rho L over 2 pi epsilon naught times 4 over 25 plus rho L over 2 pi epsilon naught and 1/4. And it would be AZ. Y'all follow me? The only thing I'm doing is adding up the components now. I get the E field from one charge source and the E field from the other charge source and sum them, right? Can you do me a favor and just tell me what the AY component is in this one? So it's rho L over 2 pi epsilon naught times 3/25. Well, 1 over 2 pi epsilon naught is 18 times 10 to the 9th times rho rho L, which is 5 nanocoulombs. Anyway, just tell me what this coefficient is for AY. And you might as well give me the one for AZ, and you're gonna find out the book's answer, or the answer I posted is probably correct. Say again?
0.78.
For which one?
AY.
0.78, did you say? Did you work this?
This matches the
0.78? 0.78 AY volts per meter, and
then 36.84 volts per meter at AZ.
36 point what?
36.84. I think the AY should be 10.78.
Oh, I'm sorry, 10.7, my bad. And these units are volts per meter. Did you all get that? How many did? All right, those are the answers, correct? All right. Now, that's a good problem, because it forces you to think about the unit vector away from that, all right? It makes you focus on that, and that will become important. The quiz today will have that kind of, they require that kind of understanding, right, being honest. Okay, other questions? Nothing? Okay, so next thing I'm going to talk about is something that makes your life easier once you get an understanding of it. It's called Gauss's law. How many heard of Gauss's law? Gauss, I got a story for you. One of my heroes. Does anybody have me before when I told this? All right, everybody went to grade school, right? I went to grade school. Went to a Catholic grade school. One thing they love at Catholic grade schools, they give us things, the repetitive tasks that bore us to death, but give time to grade papers. Like adding up all the numbers from 1 to 100. Takes a while for a third grader, second grader to do that. Gauss, of course, was at the third grade or second grade at one time, and he was asked to do that, but Gauss came up after about a minute and a half and gave him the answer, and it was right. And they were shocked. So Gauss said, if you're gonna add up any numbers, let's say it's 1 to 100, I start with 0 plus 1 plus 2 plus plus 100. Then I'm gonna add something else to this. It's gonna be 100 plus 99 plus 98 plus plus 0. Now I've got twice the sum, don't I? I'm gonna add them up. And you'll notice that each one of these columns is 100. Right? And there are 101 100s, aren't there? Y'all follow me? I was still a kid in the third grade or second grade.
Yeah.
That's why he's one of my heroes. I hated to do these things. So he said, well, I have 100 101s, and if I divide that by 2, that's the answer. And guess what? That's 50 times 101, and that was the answer, and he showed it to me. Like, I don't know if it was 100, if it was 200, whatever they gave me. And Gauss became very famous. He got pushed along, and he's probably one of the single greatest scientists, mathematicians that we've had in modern era. By modern era, that's after the time of Christ. So I'm being honest with you, that's one of the reasons he's my hero. He also is a person that was a brilliant scientist, and he, now I gotta tell you one thing that you need to appreciate. Everything that we do with Maxwell's equations and stuff, all of it are based on measurements. This is not Moses coming down from Mount Sinai with the Ten Commandments. This stuff is something based on measurements. But there's one thing about nature itself. There's an extraordinary amount of symmetry, and behavior is predictable to the nth degree. That means mathematically you can express what we observe. And this is what Gauss's law is all about. So what Gauss's law basically says is that if we have any charged system, if we have a total charge Q, no matter how it's dispersed in there, You won't see the application yet. If you close that with a closed region, some surface S, then there will be something called the D field that comes out of there that I'll get to in a second. But if you integrate the integral of d dot ds over any closed surface, it's equal to the total amount of charge enclosed by that surface. In another way, if this is called the differential, or I'm sorry, the integral form of Gauss's law, just remember that. Now, without me going into a great deal of, I'm getting all the specifics right now. This is the integral form. It's an integration. It's an integral form of Gauss's law with the D field, not with the E. But the differential form is divergence of D is equal to rho V. Now, rho V would be the volume charge density. Y'all with me on this, class? That's called the differential form. If you've never heard it expressed this way, try to appreciate it. I'm teaching you the way I would like to hear it if I was where you are, because this now is going to have some application. So what exactly does that mean? This doesn't mean much in itself unless you see it applied. So we're going to start with the simplest thing. Suppose I take a point charge and I put it at the origin, and I'll just say the point charge has a charge Q, right? Follow me? Now, I'm going to go ahead and put a surface around that, and I'm going to put a sphere around that, and that point charge is going to be at the center of the sphere. It's a thought experiment. So just assume that there's a spherical surface around that. Are you with me? Now, the total charge inside this sphere, that's sphere, and we'll call it a radius R. Well, according to Gauss's law, the total charge enclosed, which is Q, right, is equal to the D field. And the D field is going to, I didn't say this, there's a lot of things happening at once, but the D field, like the E field, the two are proportional, points radially away from the charge created. You all follow me? Remember the E field? From a charge, it always points either at the charge if it's negative or away from it if it's positive, right? D field does the same thing. It either points right at or right in the opposite direction, depending if it's plus or minus charge. And if I look at this, it's the D field, therefore it'd be in the radial direction. It'll be a function of the distance away, R, but it's times, now I could write this integration and do it, but what's the surface of a sphere? Do you remember? Surface area. 4 pi r squared. How many remember that? The volume is 4/3 pi r cubed. And I sometimes write the equation and do the integrations, but this is one of those you should know. You should know the area of a circle, pi r squared, the volume of a sphere, 4/3 pi r cubed, and the surface area of a sphere, 4 pi r squared. Those are things you should know. Times 4 pi r squared, which means the D field itself, for this case, for a single charge, is Q over 4 pi r squared, and it will be in the AR direction, radially away. Now that looks very similar to something you saw with the E field, right? The only difference is the E field has epsilon. So here's the deal. The relationship between the D field and the E field is real simple. It's D is equal to epsilon E. That's it. But here's the benefit, and you're going to see this more clearly shortly. The benefit of that using Gauss's law, for any kind of shape that's conformal to a standard geometry, for instance, spheres, all right? If we have rings of charge, well, lines of charge, things like this, we can get the D field and then get the E field without doing any kind of integration. Remember the infinite line charge, right? If we wanted to do the integration, it came down to that dx over the square root of x squared plus a squared, that's square root, x squared plus a squared to the 3/2 power that you had to integrate, right? And That integration, if you didn't know it off the top of your head, you'd have to work on it if you had to do it without a calculator in class. Take a little time. With Gauss's law, it's trivial, and I'll show you what I mean by that. We can get the D field, then get the E field just by adding a constant epsilon to it. So, I'm really trying to make it apparent why this stuff is so valuable to you guys. So let's take a look at the line charge problem, but get the answer by using Gauss's law and not by doing the hardcore integration. So here, we know the answer to this, but I'm going to have a line charge, rho L, constant charge density on some axis. You can call it the z-axis. Doesn't matter. And now, I want to figure out something about this. I want to figure out what the D field is at any distance away from this. Any distance rho away, all right? I want to know what the D field is out here. So that's my question. First thing I have to say, if it's infinite, in order to use Gauss's law and it becomes something that's useful, you have to realize you have to have insight into the actual direction of the D field based on arguments of symmetry or something like that. If you have an infinite line charge, it should be pretty apparent to you the only way for the electric field to point is away from it. Y'all with me? If you're up here, it's pointing in that direction. If you're down here, it's pointing in that direction. All right, you have to at least see that. Now, if you see that, what I'm going to do is something, remember that this is the charge density, okay? I'm just going to go ahead and I'm going to put an imaginary surface. It's called a Gaussian surface. There. And I'm going to have it so it's symmetric about the z-axis, and it's at a distance rho away. Y'all follow me on this? Basically, I got a sleeve there, right? It's a cylinder. And it's going to have a height h. Now, anytime you get to choose a dimension of a height, always choose 1. That way you can't mess it up if you forget to divide by. So I'm just going to say h is 1. That's the height of the cylinder, okay? Everybody see this so far? Now, come over here. I know that the integral of the D field over the closed surface dot ds is equal to the charge enclosed. The charge enclosed would be rho L dot dl from 0 to h. I want you to just take a look at what I'm saying. Gauss's law says all the charge inside that surface will be equal to the integral of d dot ds over that surface. Do y'all buy that? Right? And the reason I didn't write anything else is because rho L is a line charge density. When we integrate the line charge from 0 to h or over any length h, we get rho L times h, don't we, class? Right? So the amount of charge, and what did I make h?
1.
And therefore, when you integrate this, you just get rho L in terms of magnitude. Y'all follow me on that? And the reason why? Okay, now what is this integral? And here I have to talk to you about this. You see you have a top right here, right? Now, we could write down a differential surface here, and it would be rho d phi d rho. If I wanted to do it, I'm not gonna, you don't have to write this, but there would be a differential surface, ds, that would be equal to rho, and then it would be d phi d rho, and it would be in the az direction. Y'all agree it would be in the az direction? Right? So when I come over here, and I do for that top, d of the top, dot, and this would be rho d phi d rho az, I know that the D field will only have a rho component. Do y'all follow me in this? I made that claim. Do y'all see that? So if you have a rho dot az, what do you get? A rho dot az is 0, isn't it? The dot product of any two unit vectors that are orthogonal. AX dot AY is 0, AX dot AZ is 0, A rho dot AZ is 0. Y'all follow me? A rho dot A phi is 0. That means that this term will be 0. So the integral of d dot ds over the top is a non-issue. It's 0 by definition because we assume the vector d is in the radial direction. Y'all see that? Next, what about the bottom surface?
Same thing, right?
Same thing, right? Because the vector, unit vector is pointing in the minus AZ direction. Y'all see this? So there's only one integration of interest, and that's that outer surface, right? When I do d dot ds, that's what I'm about to do right here. So if I wanted to do this formally, and I've got a shortcut for you, but I'm going to take the integral now. Something I didn't say, but these are things that should be obvious. Since I'm at a distance rho, and the D field right here at this point will be the same as the D field on this side. Do you all follow me? In magnitude, right? It will be in the A rho direction. That's very useful. So now I have the D field in the rho direction, A rho, and it's dotted with ds. That's the outside of this can. You won't have to do this one. But in the outside of the can, right there, the differential surface is pointing in the A rho direction. Do you all agree with that? It's got to be perpendicular to the surface, pointing in the A rho direction, correct? Or the radial direction. Now the differential unit of surface area would be rho d phi times dz. Now if you think about it, rho d phi is that wiper arm thing here. If you're at a constant distance rho, and you wiggle it by d phi, that's how the tip moves, right? And then dz is the vertical component. So it's wiggling this way, rho d phi, dz, it's in the A rho direction. So when I go here, I put down rho d phi, dz, A rho here. This is a 2D integration, but I'm just going to ask you this. Where does dz go from? Class? 0 to h, or any value to h and any value. You with me? Over a span of h. So it goes from 0 to h. And where does phi go from? All the way around, right? 0 to 2 pi. You all with me? So phi goes from 0 to 2 pi. Now, what about A rho dot A rho? 1, yeah. So that's my integral. You'll notice I'm not integrating with respect to rho. It comes out. So now I have d rho times rho times dz from 0 to h, well that's 1, and d phi from 0 to 2 pi is 2 pi. So now I can see that d of rho is simply rho L over 2 pi rho, and because I've got a rho there, I can just do it this way and put A rho. Now, how would I get the E field from that? Divided by epsilon. You all see this? And you'll notice if we divide this by epsilon, we have what we've been talking about that we got by doing an integration over the length of the line using the Biot-Savart law. Y'all see that, class? I should say, Coulomb's law. Everybody with me on that? Now, you're going to see the power of this in a bit, but I wanted to at least expose you to Gauss's law. Remember, this is the integral form. Well, this would be total charge inside the surface, and this is, I guess I erased it, but the divergence was the differential form. It's not bad, but I've got to give you a series of problems so you can really see how this is beneficial to do for homework. How many remember Gauss's law when you're in physics? Did your professor do something like I did, explaining it? The physics professors really can do a good job at trying to explain these kind of concepts based on a lot of their insight. So it's important. We do appreciate this. And this is something that's very important in electrical engineering to understand this, electrical and computer engineering. So now, you get your quiz. So, could you spread out, get at least one empty